Thank you, Roman, for a kind introduction. It's my great pleasure to be here to talk about my experience in setting up a new lab. I actually moved to Texas State University 5 years ago from McGill, Peter Gupta's lab. And I've been spending lots of time to actually setting up my lab. So I'm going to talk about cryogenic AFM instrumentation and automation with Python API using MFLI locking. I'd like to first acknowledge my students who actually did the work. And so the first, Michelle Ford, who worked on establishing the frequency sweeper module. And then Noah Austin Bingaman, who is actually here, who actually worked a lot on interferometric measurement I'm talking about, and KPFM automatization and the LT-AFM instrumentation. And Iris Okoro, who is an undergrad student who worked on the KPFM automation, and Binod DC, who worked on LT-AFM instrumentation. So here's the outline of my talk. So first, I want to talk about what measurement I'm interested in doing, single electron sensitive electrostatic force microscopy. And then I developed, a low temperature FM setup, which is integrated in closed cycle dilution refrigerator. And then we encountered interesting problem, which is actually related to what we've discussed, like Roman discussed, how actually, Q factor influences the noise. And to do that, we had to actually come up with automated measurement of the noise. And then just touch on, a few, one more thing, actually, how to actually automate setting up the FM-KPFM, which is actually fairly complicated for undergrad student. So I've been working on this single electron sensitive electrostatic force microscopy. We call it EFM. This is a very interesting way to actually measure the quantum dot, like electronic structure of the individual quantum dot, by actually looking at the single electron tunneling between quantum dot and this conducting substrate. Basically, AFM tip, vibrating AFM tip induces single electron tunneling between quantum dot and conducting substrate, which actually causes oscillating force acting on the tip, which actually causes frequency shift and dissipation or damping. So as a result, if you sweep the bias voltage, you can actually see a bunch of those single electron tunneling peaks from which we can extract electronic energy structure of the quantum dot and the charging energy and so on. And if you scan the surface at the fixed bias voltage, you can actually observe the same thing as a bunch of concentric rings. And what's interesting is if you have multiple quantum dots which are interacting with each other, this interaction actually appears as a avoided crossing. And then we can actually study the interaction between the dots. And in addition to that, by actually looking at both frequency shift channel and the damping channel, dissipation channel, we can measure basically time delayed force, which in this case arises from single electron tunneling process. So we can actually measure the tunneling rate quantitatively by looking at both frequency shift and damping channels. So this is one example we already did in my lab. So this is the gold nanoparticle, attached to the gold substrate with a double-stranded DNA, actually 26 base pair. It's like, a short DNA chain. So the purpose of this measurement is actually you're interested in measuring tunneling rate, in this double-stranded DNA. So this is the topography of quantum dot, like gold nanoparticles, 5 nanometer diameter. And this is the dissipation image. So you can see a bunch of concentric rings, each of which corresponds to the single electron tunneling. So if you go to one of the quantum dot, and if you sweep the bias voltage like this, you can see a bunch of single electron tunneling peaks, both in the resonance frequency shift and the dissipation. And by just taking the ratio of the frequency shift to dissipation, one can actually extract the tunneling rate quantitative manner. And we measured two different sequences, like this is poly 80, all 80, 80, 80, 80. 26 base pair. And the other one is, more complex, sequences. And we can find that, tunneling rate can be actually quite different even. So we could take, a bunch of measurements and took this histogram. And if you take the, average value, then we actually saw, 277 kilohertz for this poly-AT. And the more complicated one with more GC pairs, we saw actually, an order of magnitude higher tunneling rate. So this can be measured, used as a very useful tool to measure those charge transport. So as you saw, we actually need a lot of time to do this measurement at low temperature. So then I decided to build my AFM system based on a cryogen-free dilution refrigerator system because I didn't want to worry about, liquid helium consumption. So my strategy was actually I got a very big, fridge like this, which is typically used for quantum superconducting quantum computers. So this is like really big and lots of volume inside. So then to cope with the vibration, mechanical vibration, because it's very noisy, so we actually devised this spring mass damper system. So you can see 4 springs, and this is a big mass, like 10 kilogram of mass. And the extension of the spring is almost 200 millimeter, which actually results in the vertical resonance frequency of 1 hertz, which is as good as typical optical table. And this actually works fairly well for our purpose. And then, so we haven't actually operated at very low temperature yet, but potentially, this dilution, base temperature of dilution, which is 10 millikelvin, and we have a superconducting magnet which can go up to 9 Tesla. Unfortunately, it takes a long time to cool down because of this cryogen-free nature. And so we built our own custom LT low temperature FM unit. And so we actually use the normal cantilever, not a closed tuning fork, with a fiber optic interferometer detection, because we are measuring long range electrostatic force. The tip sample distance can be like several 10 nanometers. So we need to use a fairly soft cantilever. And so then we use, actually build our own piezo stage, and so to make the microscope really rigid. So we did some trick in our interferometry system. So we used actually 2 lasers used for detection and excitation. Because we found that, actually, I show that, if you use a piezo to excite a cantilever, you get a bunch of, spurious peaks, which actually originate from the mechanical resonance of, excitation systems, which can actually show up in the dissipation signal. So that's why to get rid of this issue, we decided to implement optical excitation system. So, you can actually look at this paper for more detail, but essentially we have 2 lasers, 1 laser for excitation. So we intensity modulate this laser. Then, this optical force excites the cantilever. And another laser is just used for the detection. So this is actually important part of my talk. So as a result, if you measure this intensity versus fiber position or cavity length, then you get basically 2 different interferograms. And what's interesting is, so because the optical force, acts on the cantilever, and we have 2 lasers, and this optical force is actually dependent on the intensity of the laser light. So, since the intensity is a sensitive, changes as a function of cavity length, so it acts as an optical spring. So then, so this can change both, Q factor and the cantilever resonance frequency. And now we have 2 lasers, so the things gets more complicated. So essentially, what we are interested in is what position is actually most optimal for our measurement in terms of noise and controlling the, PLL and so on. So basically, as I just summarized, both detection and excitation laser contribute to the optomechanical force independently, and each laser can produce different optical spring constant. basically you can control, different slopes. And we have two ways to adjust the slope of each laser. One is, adjusting the cavity length. Or actually, this is possible with conventional optical interferometer setup, but this actually changes the sensitivity of detection. So we don't necessarily want to do that. We want to actually fix the position where the sensitivity is maximized for the detection. But now we have another choice, which is the power of the excitation laser, which can set the optical force, cavity optical mechanical force independently. So now we actually try to explore how one can actually take advantage of this possibility to optimize the noise. So to do that, we need to automate the measurement because it's very lengthy measurement. So before talking about that, I want to introduce my setup. So we use, MK3PL signal ranger with GXSM, the open source, software. And we use, of course, Zurich Instruments MFLI lock-in for PLL and the PID and the data acquisition. So we use basically signal ranger with GXSM for image acquisition and distance feedback and scanning and piezo coarse positioning. And MFLI for PLL to provide excitation signal and measure the frequency shift and dissipation. So this is a block diagram. So, I don't really need to explain, but basically the output of MFLI goes to this optical box that I already showed you. So this is exciting the, basically this modulate the intensity of excitation laser. Then we can, this modulated laser go to the cantilever and it excites the cantilever. And also this, one of the outputs of this signal range electronics basically provides a sawtooth wave to move the, this Z fiber, the fiber motor to adjust cantilever fiber distance. So this is the first, sort of module which we use with the Lab1 Python API. So this is just a simple module which can actually do the frequency sweep to measure the resonance, and it can, we can get the quality factor, and we can set the resonance frequency automatically. Otherwise, we have to copy paste this in the standard Lab1. So, and of course, we have a possibility to include other automation features like, setting up the PLL and AGC or even KPFM eventually. So for the measurement of the noise as a function of this cavity, length, what one has to do is, so we, at each fiber position, we need to record the interferometer outputs for detection and excitation lasers. This is necessary to set the sensitivity and then perform frequency to measure the Q factor, because we need to know the Q factor to set the PLL and resonance frequency, of course. And then setting up the PLL and AGC with measured Q and resonance frequency as just Homan did, and then close the PLL and AGC loops. And then using the MFLI data acquisition function, we acquire the frequency shift and dissipation signal to measure the noise. Then turn off the cantilever excitation, and we wanted to actually measure the thermal noise to measure the temperature of the cantilever, and save the data. And then move to the next fiber positions. So doing this is actually quite a lengthy process, and it can take long time. And it's very error prone if you do it yourself. So then we decided to automate. So actually Noah wrote the code because, he didn't want to, be in the lab overnight, so the experiment can take up to easily 24 hours. So the automation is critical. And so we needed to control MFLI and GXSM, like signal range electronics, within the same Python script. That was a tricky part. And to control GXSM from a Python script, we implemented a local socket server running a GXSM's built-in Python console. So the main Python script can send the text strings to GXSM to do, actually in our case, we want to actually move the fiber. That's the only thing we want it to do. And then this server, once the server receives this command strings, it executes the command. In this case, the move the fiber. Then, of course, we can control the other functionality of MFLI straightforward manner with the Python API. So this is just a piece of code which is running in the GXSM built-in Python console. So it's a very small piece of code which actually just we need to run. And then, so this is a Python script command, GXSM. So this is a part of the code which we send the command. It's like this. We can send the command to that Python server. And then, I don't need to really, okay, so this is the part, where we control the MFLI. So this is standard, Python API. So you can set the PID parameters, all the parameters, and we can, close the PID and so on. So it's relatively straightforward. And here's the result. So we get, these two interferograms. So the blue one is excitation laser, and this orange one is a detection laser. So as you see, okay, so here we focus on 4 fiber positions. So position 1, so you can see detection laser is almost slope is 0. So this is not ideal for detection operation usually, but just for testing purpose, we did the measurement here. And the slope of this excitation laser is like negative. And here, position 2, slope of excitation laser is almost 0. So when you change the average power of excitation laser, we don't expect to see much change in both Q factor or resonance frequency. And 3, since slope is opposite to the position 1, so effect will be opposite. And the position 4, again, the slope of excitation is almost 0, so we don't expect much when you change the average power of the excitation laser. So look at the result here. So at position 1 here, as you increase the optical power from 66 microwatt to 2022 microwatt, actually Q factor goes down a lot. And resonance frequency goes down a little bit, just a little, a few hertz. And position 2, so Q factor remains almost the same as expected because the slope is almost 0 here. But the resonance frequency shifted almost as much as this position 1, which is kind of strange. And position 3, now opposite happens. So so this blue one is a lowest optical power, and as you increase optical power, Q factor actually gets enhanced. And the resonance frequency strangely remains the same because it's supposed to go up a little bit. And position 4, as we expected, nothing really changes, which is okay. So then we were kind of puzzled why this happens, why resonance frequency actually shifted. And then, okay, so this is just the same thing, but just extracted the Q factor as a function of optical power. So at position 1, Q factor decreases, and position 3, Q factor increases. And the delta F resonance frequency, goes down with this, field circle. And this orange one is a raw value. So field triangles is a raw signal. So it's not supposed to change, but it did. So it turns out that this unexpected frequency shift is due to the absorption of the light due to the cantilever. So that cantilever actually gets heated slightly, and then that actually shifts the resonance frequency downwards. So actually, Noah did the COMSTOL calculation, assuming certain optical power absorbed at the tip of the cantilever. And so, we assume the 4 Kelvin. And then, so this red line is basically temperature. So temperature actually increased like 0.8 Kelvin from zero power to 2 milliwatt power. And correspondingly, so using the temperature dependence of the Young's modulus, we could calculate the change in the eigenfrequency. So it's shifted by only F parts. So basically, using this simulated value, we corrected for this data. So this purple one is corrected frequency shift. So now once we correct for this in temperature-induced frequency shift is almost non-existent. And at this position 3, you get basically larger, like positive frequency shift. Gross frequency shift almost looked zero, but actual corrected one showed increase in the resonance frequency. So yeah, so then it's good because now we know temperature actually slightly increased, so we could actually measure the change in the temperature of the cantilever. And so what's nice is now by using, because we have now frequency shift and damping, or correspondingly optical spring constant, and the damping optically induced damping. So using two informations, we call it delta gamma for the damping and delta K for the spring constant, we can actually extract the delay time, because the fact that we see the change in the Q factor means you have a delayed force. And this delay time can be just calculated by taking the ratio of this damping to the resonance frequency shift. And once you get that, you can actually calculate this slope of this optical force. And this is the result. So so this is extracted spring constant for different positions, position 1, 2, 3, 4. So position 3, 4, we don't get much optical spring constant. And the time delay is almost like 1 microsecond, regardless of the positions, like 60-degree phase delay for this 160 kilohertz cantilever. And so then if you compare these extracted spring constant, optical spring constant, 0.5 to 1.25 millinewton per meter, then we compare it with expected value for just assuming radiation pressure force. And it turns out that optical radiation pressure force can account for only 4%, which makes sense because we are using very low finesse optical cavity, so cavity ring down time does not account for the time delay we need to explain this Q factor change. So basically, what we learn is optical absorption, like photothermal force, really dominates this process. I can skip that. So the next topic is the automation of Kelvin probe force microscopy, particularly FM-KPFM. So we've been actually interested in measuring this Moire potential on twisted hexagonal boron nitride multilayer. So this Moire physics is getting really emerging these days. And so actually Noah is going to talk about this Kelvin probe study on Wednesday. So I'm not going to talk about the detail, but basically this Moire electric static potential, which actually looks like this. So this is a topography of stacked HBN, twisted. So twisted means, there is angular misalignment. And, in that region actually shows very beautiful periodic electrostatic potential, which is due to the periodically, changing electric dipole. So we do a lot of, KPFM measurement of this HBN. Then, I want basically, graduate students and undergraduate students to do this measurement. But then we face an issue. So because, we use, other AFM, which is also custom built, and control electronics is essentially the same. So, GXSM plus, MFLI. So there's a very steep learning curve. So this is, MFLI, so block diagram of MFLI. So we use a self-oscillation controller in this measurement. And then, we use PID1 for PLL, and PID2 for AGC, and PID3 for, FM-KPFM. So basically, students need to actually learn how to, click all the things properly in the proper order, which is not really trivial. So let me just, show the steps, like procedure, basically, the students need to learn. So first, we have to learn how to actually set up the self-oscillation, which is not easy. But, assuming this is done, so students need to approach the tip with the DC bias. So this is GXSM part. And then we have to apply AC modulation voltage for KPFM. So you have to set, frequency and amplitude, and you have to click add button in the MFLI control panel. And then the crucial part is optimize the demodulator phase to maximize X output for KPFM feedback. So to do that, one has to first reduce the demodulator bandwidth to get a stable reading. This is crucial. Otherwise, phase is not really reliable. And then just perform auto phase adjustment, just click a button, but you still have to do. And then don't forget to return to the original demodulator bandwidth. If you leave, the very low bandwidth, KPFM won't really work. And then because, so this is tricky part because, this KPFM and, distance feedback basically, interact with each other. So before turning on the KPFM, you have to turn off the distance feedback. So you have to actually go to GXSM and then turn off KPFM feedback. You have to set the proper PI gains. This has to be done in MFLI. And then because we cancel the electrostatic force, frequency shift actually decreases to the new value. So if you want to keep the same distance, you have to actually change the set point in the GXSM. Then finally, you can turn on the distance feedback. So this is very complicated for most of people. So we wanted to really, automate this process. So then basically, student, NOAA and undergraduate student actually work together to, write a piece of code to automate this. So here, for example, you can control the bandwidth of the demodulator to the new value. It's very straightforward. And then you can do the, automatic phase adjustment like this. And then you return to the original value. And then, we use the same trick to control the GXSM. You can turn on and off the GXSM, distance feedback control. So right now, so this is, the piece of basically the module. So we can set the, modulation frequency, amplitude, and so on. So now, instead of doing all of them manually, we can just click, I think, this run phase adjustment button. So this is just to show, the effect of this script. So this is, frequency shift versus, bias voltage curve. And this orange one is, X output. So we want to basically have, max positive slope with the maximum slope value. So after running this, script, basically clicking one button, you can get, this orange one. And then KPFM actually works well. So this is what we did, with the LabVIEW API. So the conclusion is Lab1 Python API enables the straightforward automation of complex and lengthy measurement and the automation of complicated experimental setup. And automated measurements really enables a quantitative understanding of the cavity optomechanical effects in the low temperature AFM. And now setting up FM-KPFM experiment is now possible for like undergrad students.